Hi everyone, welcome to today's lab demonstration video. Hope you're all doing well. Today we'll be going over the synthesis of aspirin through an esterification reaction. So a little bit about the relevance of this week's experiment. Aspirin is one of the most widely used medications throughout the world. The history of aspirin began when people started to investigate the therapeutic properties of the bark found in willow trees. In 1763, Edward Stone was the first person that discovered that the bark found in willow trees could be used to treat many of the symptoms found in malaria. Later on, it was discovered that the active ingredient in willow bark was salicylic acid. And although salicylic acid began to be widely used as a therapeutic treatment for malaria, its use was limited by the fact that it suffered from severe irritation side effects. Later on, in 1893, a German chemist by the name of Felix Hoffmann, who was working for the German company Bayer, devised the practical synthesis of acetylsalicylic acid, or aspirin. The importance of this discovery is that aspirin was able to maintain the therapeutic properties of salicylic acid, however, it did not suffer from these horrible side effects. It should be noted that although Felix Hoffmann was not the first person to synthesize acetylsalicylic acid, his work is widely credited as being instrumental for the use of aspirin as a therapeutic agent. However, a quick side note, today there's still a lot of controversy surrounding the fact of whether Felix Hoffmann was actually the one that came up with the idea to synthesize aspirin as an alternative to salicylic acid. A lot of scholars today argue that it was actually one of Hoffmann's co-workers, Arthur Eichengrun, who played a large fundamental role in the development of aspirin and its use as a therapeutic agent. The reaction that we'll be conducting today is an example of an esterification reaction. As you guys have seen in lecture and even previous experiments, there's a lot of different types of esterification reactions. Earlier in the semester, we showed you guys the synthesis of benzocaine, and that was going through a Fischer esterification mechanism. So for today's experiment, if you notice, we're forming an ester starting from a phenol. But if we try to do a Fischer esterification reaction, we would probably get a lot of unintended products because if you notice, our starting material also has a carboxylic acid in it. So instead, we're going to use an acylating agent, which will be acetic anhydride. And you can think of that kind of like a carbonyl group with a very good leaving group. So I'll show you guys the mechanism for that as well. We start by activating the carbonyl group in acetic anhydride. Then that allows the phenol group in salicylic acid to attack this carbonyl group. And then after doing some proton transfer, we can eliminate acetic acid, and that gives you your desired product. Alright, so now we'll start the lab demonstration video. Okay, we're starting out weighing the salicylic acid. We got just about 2 grams, 2.001 grams, and then you can see that it's a white powder. Next, we're going to measure out the acetic anhydride. We're going to try to get as close as we can to 4 milliliters. And make sure you don't forget to calculate the grams of acetic anhydride based on the density.
So we just weighed out 2 grams of salicylic acid. So I'm going to add that to an Erlenmeyer with a little stir bar. We have our 4 milliliters of acetic anhydride, so we'll add that. And then we'll set that in the bath to heat. The bath is currently reading about 50 degrees. And we need to make sure we add our 2 drops of concentrated sulfuric acid to catalyze this reaction. That might be helpful. So it's been about 15 minutes, so we're going to take out our reaction.
I think this is good.
Okay. So we can see little white pieces that seems to have precipitated, so that is probably our product. We'll cool this in an ice bath. And then we'll add 50 milliliters of water. While we're letting that cool and recrystallize, I'm going to start heating up some ethanol for the recrystallization to purify the crude product we'll get from this. So I'll start heating up some ethanol, and then once I add the water, I'll heat up some water as well. After a minute or two, it's solidified. So we're going to add our 50 milliliters of water so we can do our vacuum filtration.
Good.
So I've mixed up and broken up that chunk of our crude product in the water, and I'm now going to filter that. So I've wet the filter paper with a little bit of deionized water to keep it in place. And I'm just going to carefully pour into the center of that mass. Now I'm going to let this dry under vacuum for a couple of minutes. Okay. So our ethanol and our water have heated up, and it's been about 5-10 minutes. So our crude product should now be dry. So I'm just going to transfer it into much quieter. I'm going to transfer it into a small Erlenmeyer so we can do our recrystallization. So we have a nice white crystalline solid, and there's definitely a vinegary smell to it. So we know in this reaction we'll be creating acetic acid, which is just vinegar. So that smell is probably from a little side product. So I now have a good amount of product in an Erlenmeyer. So for recrystallization, we're going to do something a little different than normal. What we're going to do is we're going to dissolve our crude product in a minimum amount of ethanol, of warm ethanol. Then we're going to add a minimum amount of warm water to the still heated, just solubilized mixture until it starts to precipitate out and get cloudy. And then we're going to cool that down. And based on what the lab manual has told us, it'll take about twice as much water to ethanol. So we're going to want to make sure that we keep track of how much volume we use for each of these two solutions. So we're starting with about 50 milliliters of ethanol. That'll make it easy to tell. And nope, but it's got most of it, so. Okay, so we're starting to get most of it dissolved. I'm going to heat this just a little bit longer. Make sure it stays warm. See if it all dissolves. Okay. So it took about 2 pipettes. Pipette is approximately 1 to 1.5 milliliters. So it took probably about 2 to 3 milliliters of ethanol to dissolve. So we're going to use approximately twice that in water. So I'm going to add a little slower just to make sure that we get that just precipitation point. So we've added approximately 2 milliliters of our ethanol and approximately 10 milliliters of water. So that's quite a lot of water. So we're going to try to recrystallize this out. So we're going to let it cool down to room temperature. And then we'll throw it in the ice, or put it in the ice bath and see if we can't get some crystals. So our solution has come down to approximately room temperature, so we'll throw it in the ice bath. So we can see that it's getting cloudy, so we know that it's starting to precipitate out, which is good. So we'll leave that undisturbed for another couple of minutes as we clean up what we have. So it's been about 10-15 minutes, so there's a nice solid that we can see of our purified product. So I'm going to set up the filtration, and then we'll do the ferric chloride test. I've already pre-wet this with a little DI water. Now I'm going to grab some DI water, some cold DI water, and rinse this to make sure that we're getting a nice clean product. So we're going to be adding ferric chloride. This is going to be to test for phenols. So remember, our starting material has the phenol that we then acylated with the acetic anhydride, so we should expect to see a color change for the starting material, but not for the pure aspirin or our product. If we add a drop, we see a nice color change for the salicylic acid. We do not see a vibrant color change for the pure aspirin. And we see a minor color change for our product. So what this probably means is that our reaction did not go fully to completion. And we could validate this with the melting point in IR.